Okay, we are recording. Okay, welcome everybody to our second in our series of 8 Steps to a Jersey Friendly Yards webinars. Tonight is Start with Healthy Soil, presented by Becky Laboy. Becky is the Education Outreach Specialist with the Ocean County Soil Conservation District. She's also co-chair of the local chapter, Jersey Shore chapter, I shouldn't say that, Jersey Shore chapter of the Native Plant Society of New Jersey. She has 20 plus years experience as an educator, and she also is an avid birder. So thank you, Becky, for being with us tonight.
Great. Well, thank you very much, Karen, for inviting me here. I'm very excited to be here. Thank you, Sue. Thank you, Christine, my colleagues in Jersey Friendly Yards. So I am going to get started presenting my program, Start with Healthy Soil. Start with Healthy Soil is step 2 in the 8 Steps to a Jersey Friendly Yard series, leading to a healthy yard, a healthy garden, and healthy landscape, and a healthy environment. And as Karen said, I'm the Education Outreach Coordinator with Ocean County Soil Conservation District, and the district is a proud partner in the Jersey Friendly Yards Initiative, along with Rutgers Cooperative Extension of Ocean County, and spearheaded by the Barnegat Bay Partnership. The district has been involved in the Jersey Friendly Yards program since the launch of the website, and our low maintenance landscaping guide was an inspiration for the 8 steps to a Jersey Friendly Yard. And this guide is available on the district's website at this address shown below. And I believe Karen or Sue is going to put that in the chat. Healthy soil is the foundation of all life on Earth. Soil is the underpinning of terrestrial ecosystems and the source of a wide range of critical ecosystem services. Soils harbor an enormous portion of the Earth's biodiversity, from microscopic bacteria, protozoa, and nematodes to arthropods, as well as both small and large mammals, reptiles, and amphibians. The soil substrate houses fungi, water, and nutrients to support the growth of plants, which in turn provides habitat for wildlife, food for animals and people, clothing, medicine, and building materials. Soil manages the storage and release of nitrogen, phosphorus, and potassium nutrients. With the help of soil organisms through biogeochemical processes, these nutrients become available to plants. Soil can regulate the distribution of rain or irrigation water between infiltration and runoff, and it regulates the flow and storage of water and solutes, which include nutrients, pesticides, and other compounds dissolved in water. When soil is healthy and functioning properly, the soil partitions water for groundwater recharge and for use by plants and soil animals, and erosion and runoff is minimized. Soil acts as a filter and a sponge to protect the quality of water, air, and other resources. Toxic compounds or excess nutrients can be degraded by soil microbes or otherwise made unavailable to plants and animals, as long as we don't treat our soil like dirt. Soil protects archaeological treasures and provides support for human structures and for our gardens. Importantly, Soil is the foundation of our Jersey-friendly yards. So before we dig into our relationship with our garden soil, let's explore soil's origins. Where does soil come from? Soils are formed by 5 major factors. Parent material, the primary materials from which all soils are formed. Climate, temperature and moisture affect rates of biological activity and chemical reactions within the soil. And topography and relief. The location of the soil in a landscape can affect how climatic processes impact it. Soil organisms. Each soil has a unique combination of microbes, plants, animals, and humans acting upon it. And time. All of the other factors assert themselves over a period of time, hundreds and thousands of years. The influence of each of the 5 major factors varies from place to place, but the combination of all 5 factors will determine the kind of soil developing in any given place at any given time. New soils increase in depth through deposition of minerals and organic matter. Layers in the soil, called horizons, show the development of soil over time. Soil horizons are layers in the soil, typically parallel with the soil surface, whose physical, chemical, and biological properties are each different from the layer above and below. The O horizon, the organic layer containing humus, is thin in some soils, thick in others, and sometimes non-existent. The A horizon is the topsoil, which contains both humus and minerals. Some soils have an E horizon called the eluviation layer, which contains leached minerals and leached organic matter. The B horizon is the subsoil containing mostly minerals. And below the B horizon is the C horizon, which is the broken down parent material, containing mostly weathered rock. And below the C horizon is the R horizon, the unweathered parent rock. Although New Jersey is a small state, the formation of soil in New Jersey is quite diverse based on our geographic location. And that's because our state's geologic history is quite diverse. New Jersey is divided into 4 physiographic provinces, each with distinctive rocks and landforms. The Ridge and Valley is to the north, and then the highlands, Piedmont, and the coastal plain encompasses all of South Jersey. The Ridge and Valley is underlain by faulted and folded sedimentary layers of sandstone, shale, and limestone that range in age from 570 to 345 million years old. And these rocks originated as sand, mud, and lime sediment deposited in former seas and floodplains. Over long periods of time, through compression and folding, these once flat sedimentary layers were thrust into faults and tilted, emerging above Earth's crust as observable outcrops of bedrock. Erosion of the shale and limestone creates the valleys characteristic of this province. Highlands is our most ancient province, formed during the Precambrian era about 1 billion years ago. Melting and recrystallization of sedimentary rocks were deeply buried, subject to pressure and high temperatures, creating metamorphic rocks such as granite, gneiss, schist, and marble. Granites and gneiss resist erosion and create highlands, and belts of exposed sedimentary rock weathered to create valleys and streams. A series of faults separate the Piedmont from the highlands. And in the Piedmont, sedimentary sandstone, shale, and conglomerate.
I found this on the web for its faults separate from the highlands. Check it out.
That was my phone answering my question, or trying to answer a question. I apologize for that. The coastal plain, let's see, Piedmont. We're on the Piedmont. We're talking about sedimentary sandstone, shale, and conglomerates that create a broad lowland interlaced with some igneous basalt and diabase, which create the ridges and uplands. And these were formed during the Jurassic and the Triassic ages, about 200 million years ago. The coastal plain province consists of sediment, which ranges in age from the Cretaceous period to the Holocene, which is between 135 million years ago to the present. And sediment consisting of sand, clay, green sand, and gravel are deposited as the ocean undergoes transgression and regression, so rising and falling. And rock is an aggregate of two or more minerals. So minerals include feldspar, quartz, gypsum, talc, mica are some that you may be familiar with. And minerals are, of course, made up of elements. So for example, the rock granite mostly consists of quartz and feldspar minerals. And then feldspar contains the elements sodium, calcium, and potassium. And as you may know, calcium and potassium are important nutrients for plants. And these nutrients are leached out of the rocks and minerals through the process of weathering and erosion, which tear down the surface of the earth, and nothing can escape it. Climate exerts an important influence on weathering. However, weathering also synthesizes new minerals that influence important properties in the soils. The nature of the rocks and minerals being weathered determines the rates and results of the breakdown and synthesis. And physical weathering processes occur through disintegration by either temperature or abrasion by water, ice and wind, or by plants and animals. And water wears away the sharp edges of the rocks. Water freezes and cracks of rocks, breaking them apart. Wind-blown dust and sand can wear down rocks by abrasion. Rocks exposed to sunlight might heat up during the day and cool down during the night, causing alternate expansion and contraction of their constituent minerals and eventually causing the rock to break apart. And plant roots sometimes enter cracks in rocks and pry them apart. And that also results in some disintegration. And then, of course, the burrowing animals might help with disintegrating rocks somewhat. And then the loosened material and the soluble products are carried away by wind and water and ice and gravity. And chemical weathering also plays a role in breaking down rock. So for example, carbon dioxide dissolves in water to produce carbonic acid in a process called hydrolysis, which, for example, dissolves feldspar into clay minerals. And microbial activity also plays a role in weathering of rock. So fungi and algae, they live in a symbiotic relationship called lichen. And the fungi release the chemicals that break down the rock into minerals, which are then consumed by the algae. So both the physical and the chemical types of weathering occur together, and each tends to accelerate the other. So these mineral particles become an important component in soil. In fact, nearly half of soil by volume is mineral particles. And air and water together fill the pore spaces in the other 50% of soil composition. And between 3 and 5% of soil is organic matter. So let's take a look at this information in the context of the physical, chemical, and biological properties and processes that support healthy soil. The mineral particles are categorized by their size, and this is called the soil's texture. Sand particles are the largest, and you can actually see a single grain of sand with your naked eye. You can roll it around in your hand, you can feel it between your finger and thumb, and you can feel its pointy edges. And sand is composed of the mineral quartz, which is very resistant to weathering. And then next is silt. And silt is so small that you need a microscope to see one silt particle. And a handful of silt feels like dry cake flour between your fingers. And then the smallest particle is clay. And you need an electron microscope to see a single clay particle. And clay actually feels a little bit sticky to the touch when wet. And then anything larger than sand is considered gravel and not considered to be a component of soil. Mixtures of sand, silt, and clay are classified according to the soil texture pyramid. Along each of the three edges of this triangle, you see sand at the bottom, clay to the left, and silt to the right. To determine the texture of soil you have, you calculate the percent of each. For example, if your soil sample is a mixture of 40% sand, you find 40% along the bottom of the triangle and draw a line using the pattern of the grid. And let's say our soil sample also contains 40% silt. So find 40% along the right side of the triangle and draw a line using the grid. And our percentage needs to equal 100, so our clay content would be 20%. And then you find 20% along the left side of the triangle and draw a line using the grid. And where those three lines intersect indicates your soil texture type. And so in this case, we have loam. So how about 60% sand, 15% silt, and 25% clay? What soil texture would that be? 60% sand, 15% silt, 25% clay. We have a sandy clay loam. One more. How about 10% sand, 45% silt, and 45% clay? So 10% sand, 45% silt, and 45% clay. We have a silty clay as our soil texture type. How can you find out the texture of your garden soil at home? You can do something called a jar test and measure the percentage of sand, silt, and clay in your soil. You fill a jar about halfway with your soil sample. Then you fill the jar about 3/4 of the way with water, and you put the lid on, you put it on tight, and you shake, and then you let the jar sit still. And in about 1 minute or less, those large sand particles are going to settle to the bottom. And in about 2 hours or so, the silt particles will form a layer on top of the sand. And then you'll need to wait about 24 to 48 hours for the clay to settle out. The clay takes a long time to settle out because the tiny clay particles hold a negative charge. And when the tiny clay particles come close to each other, they are repulsed by each other, prohibiting them from joining together and forming heavier aggregates and then settling to the bottom. So it does take about 24 to 48 hours or so for the clay particles to finally settle to the bottom of your jar, and they'll make that third layer on top of the silt, on top of the sand. So once they do settle, you're going to use a ruler to measure the height of the sand and the height of the silt and the height of the clay in millimeters, and you're going to add up the total. And then you're going to turn your millimeters into percentages by dividing each amount by the total amount and then multiply by 100. So if your sample measures 30 millimeters of sand, 22 millimeters of silt, and 25 millimeters of clay, that total is 77. And then divide each amount by 77 and then multiply by 100. And then you'll use your soil texture triangle to determine the soil texture type. I realize our photo here doesn't exactly match our calculations at the top. So if we have 39% sand, I'd add that to my soil texture triangle. And then 29% silt, I'll draw my line. And then 32% clay, and together they equal a clay loam. And then one thing I haven't yet told you, how do you take a soil sample from your garden? I promise it's not too difficult. And here's a link at the bottom of the page. And Karen's going to put that in the chat. And that's a great short video that shows you step by step how to take a soil sample from your yard. And this link is also found on the Jersey Friendly Yards website on the Step 2 Start with Healthy Soil page within the 8 steps to a Jersey Friendly Yard series. So once you take your soil sample, you can conduct this jar test yourself, or you can send your sample to the Rutgers Soil Testing Lab, and they will conduct a test. They'll actually conduct a sieve test and tell you exactly what your soil texture is. So what difference does texture make? Why do you need to know your soil texture? Well, soil texture determines the amount of water a soil can hold, the rate of water movement through the soil. Soil texture helps determine the structure of soil, and soil texture also contributes to a soil's fertility. Different plants prefer to grow in different soil textures. For example, for those of you with clay soils, try planting black-eyed Susan, New England aster, and stiff goldenrod, who all do well in soils with high clay content. And those of you with very sandy soil, how about goat's rue, a beautiful woodland sunflower, or butterfly weed, who all do well in soils with a high sand content. Soil texture is considered a physical soil property, along with soil composition, soil structure, and soil color, all physical soil properties. These soil properties influence soil processes that affect plant growth and plant diversity and root proliferation and organism movement in the soil, organic matter content, aeration, water storage, and water movement, the soil's ability to resist erosion, and the soil's ability to resist compaction. So let's take a closer look at a few more physical soil properties and processes. When sand, silt, and clay soil particles combine together, they take on shape and they form clusters that are called soil aggregates. And the soil aggregates are held together by organic matter, which is bits of dead and decomposed plant and animal matter. They're also held together by water, soil moisture, and they're also held together by secretions from plant roots and microbes in the soil, which all act like soil glue. So recall that 50% of soil is solids and 50% of soil is pore space. The pore spaces between the aggregates provide places for retention and exchange of air and water. Optimum aggregates have a wide range in pore size distribution, And this includes large and medium-sized pores between the aggregates and smaller pores within the aggregates themselves. The way in which aggregates are arranged is called soil structure. Soil scientists recognize several different structure types, including these shown here: granular, blocky, lenticular, platy, wedge, prismatic, and columnar, and a few structureless types, including single grain and massive. A more granular structure is the result of a sandy soil, which tends to have poor aggregate stability. But to maintain good soil structure, avoid tilling your soil. Tilling breaks up the aggregates that have taken a long time to form. Refrain from driving over your soil, especially heavy lawnmowers, especially when your soil is wet. This causes compaction, reducing the pore spaces and thereby reducing the ability for air, water, and organisms to move freely throughout the soil. How do you improve your soil structure? Nature's miracle solution, organic matter. Organic matter, although least in overall percentage in the composition of soil, only 3 to 5%, organic matter is necessary for properly functioning soil. So let's zoom in to that 3% slice of the soil pie. The overall composition of organic matter includes between 33% and 50% actively decomposing organic matter. That's the purple slice of this pie, meaning organic particles that are in the process of breaking down. And it also includes about the same amount, 33 to 50% stabilized organic matter, meaning organic matter that has been completely decomposed, which is called humus, and that's the pale yellow slice of the pie. And these two components make up the bulk of organic matter. And then fresh plant and animal residue, so think newly fallen leaves or recently deceased arthropods, make up about 10% of organic matter. And then living organisms make up less than 5% of organic matter. And that can include any of the soil biota as well as living plant roots. And although organic matter is a small piece of the soil pie, the contribution of organic matter to healthy soil is enormous. Organic matter provides pore space. It promotes soil aggregation. It promotes storage and recycling of nutrients for plant use. It improves soil structure. It increases filtration and water holding capacity. In fact, organic matter holds 18 to 20 times its weight in water. And organic matter supports not only the physical properties of soil, but also biological and chemical processes, including provisioning food and shelter for soil organisms. And it increases something called the cation exchange capacity. So we're going to talk a little bit more about all of these biological and chemical processes. Soil is alive. Soil microbes and soil macroorganisms are critical to healthy soil. They naturally suppress pests. Soil microbes decompose that organic matter and they convert otherwise unusable forms of nutrients into forms that plants can use, while at the same time creating a soil that is porous and permeable. Increased consumption of nutrients by soil organisms prevents leaching, so it prevents the nutrients from infiltrating deeper into the soil out of reach of plants. And it keeps the nutrients available to those plant roots. And the byproducts left behind by these organisms, they act as that soil glue that increases the aggregation and thereby increases infiltration and prevents erosion. So just as we need biodiversity in above ground ecosystems, diversity of soil organisms keeps the soil ecosystem functioning at optimum health. 1 cup of healthy soil contains 200 billion bacteria. So bacteria are those single-celled organisms that feed on other organisms in the soil and decompose the organic matter. Some bacteria fix nitrogen, providing plants with this otherwise unavailable nutrient. Bacteria enhance the soil structure. They improve water infiltration and water holding ability of the soil. They compete with disease-causing organisms. They can also filter and degrade pollutants. And before plants can become established on fresh sediment, it's the bacterial community that establishes first. In 1 cup of undisturbed soil, there is 1 million meters of fungi. So fungi are multicellular organisms, and you're probably familiar with mushrooms and molds, although yeast is a single-celled fungi. And there are many others that live underground in the soil. They grow as long strands or threads called hyphae that can be several yards long. They push their way through soil particles and past roots and past rocks. They sometimes group into masses called mycelium. And fungi decompose complex carbon compounds. And they improve accumulation of organic matter, retain nutrients in the soil. They bind soil particles into aggregates, which helps to increase water infiltration and soil water holding capacity. And they compete with plant diseases and decompose certain types of pollution. 1 cup of undisturbed soil has 20 million protozoa. Protozoa are microscopic. They are also single-celled organisms, and they eat the bacteria. The bacteria contain more nitrogen than the protozoa can utilize, so some is released to plants in the form of ammonium. And protozoa prevent some pathogens from establishing on plants and function as a food source for nematodes. In 1 cup of undisturbed soil, there is 100,000 nematodes. So nematodes are small and tiny. They are unsegmented roundworms, and they live in the little water films within the large pore spaces in the soil. They feed on bacteria, and they feed on fungi, and they feed on each other. They distribute the bacteria and fungi through the soil as they move around. Some do cause some harm by feeding on plant roots, but predatory nematodes consume those root-feeding nematodes and even prevent their access to the roots. Most kinds of soil nematodes do not parasitize plants, but they're beneficial in the decomposition of organic matter. These nematodes are often referred to as free-living nematodes. Soil around small plant roots and root hairs is a particularly rich habitat for many kinds of nematodes. 1 cup of undisturbed soil has 50,000 arthropods. Arthropods are small animals such as insects, spiders, and mites. They range in size from microscopic to several inches long. They live near the soil surface or in the upper 3 inches of the soil. Arthropods improve soil quality by creating structure through their burrowing, by depositing their fecal pellets, controlling disease-causing organisms. They stimulate microbial activity, and they enhance decomposition by shredding the organic matter and mixing it up into the soil. They regulate healthy soil food web populations. And then earthworms. And in 1 cup of undisturbed soil, there's 1 earthworm. And earthworms feed on organic matter. The nutrients that are in this organic matter are changed as they pass through the earthworm's gut. And the earthworm casts are richer in nutrients than the surrounding soil and are in forms that are more available to plants. The burrows create passages for air, water, and for roots, allowing the plants to grow deeper roots, which recharges the lower layers of soil with air. And the mucus of the skin of the earthworm, as well as the castings of the earthworm, they aid in the formation of the soil aggregates as well. So by increasing the organic matter content in your soil, the earthworms can then greatly increase the water holding capacity of soils. So encourage earthworms to come to your yard or garden by either adding organic matter, and you can do this by leaving grass clippings when you mow, by leaving some leaves, and by adding compost. So earthworms and other soil organisms are destroyed by tillage, so like farm field tillage. So deep and frequent tillage can actually reduce earthworm populations by as much as 90%. And then of course, chemicals have toxic effects on earthworm populations and other macroinvertebrates. And those earthworms and those other macroinvertebrates may be consumed by songbirds. And we certainly don't want these baby robins to be eating any poisonous chemicals. In a typical soil food web, the plants are in control. And why is that? It's because the plants make their own food from the sun's energy. So food webs start with the plants. And we often think of plants taking up nutrients through root systems and feeding the stems and leaves or flowers. However, a great deal of that energy that results from photosynthesis in the leaves is actually used by plants to produce chemicals they secrete through their roots. And these secretions are known as exudates. In the rhizosphere, and the rhizosphere is an area in the soil, it's an area of interaction between the surface of a plant root and the area surrounding that plant root. Root exudates are in the form of carbohydrates and proteins, which attract and grow specific beneficial bacteria and fungi living in the soil that subsist on these exudates and the cellular material that's slawed off as the plant's root tip grows through the soil. Bacteria and fungi are then eaten by the bigger microbes, such as the nematodes and the protozoa. The waste secreted by these microbes can be readily absorbed by the plant roots in the rhizosphere, the site of root nutrient absorption. Soil life, soil biota, compete for the exudates, and they compete for the water and mineral content in the rhizosphere. There's the exudates. Each above ground ecosystem is supported by a different soil environment, which supports a different set of soil organisms and different food webs. For example, ants are the heavy lifters in the dry, sandy pine barrens ecosystem. Let's talk a little bit about soil chemistry. Chemical processes in soil determine nutrient availability to plants, support nutrient storage and release, promote soil reactions, and relate to something called the cation exchange capacity, which I mentioned earlier in the organic matter content area. and we're going to talk a little bit about that. Soil contains many nutrients, and nutrients have positive or negative charges. These are called cations and anions. Cations hold positive charges, and anions hold negative charges. For example, in this image, you can see calcium, magnesium, potassium, sodium, and hydrogen, all cations. And remember our smallest particles, which are clay and humus, little bits of organic matter, they also carry a charge. And humus and clay can bond with and hang on to nutrients through their charges. So clay and organic matter carry a negative charge, and so they can hang on to those positively charged nutrients. And the surface area of plant root hairs also contain their own electrical charges. So nutrients are absorbed by plants through cation exchanges. Anytime a plant's root hair penetrates the soil, it may exchange its own cations for those mounted on humus or clay particles and absorb the cation nutrient as nourishment. Plant roots use a hydrogen cation for the exchange. They eject one hydrogen cation for every cation nutrient absorbed. This is the way plants, quote unquote, eat. The area within the rhizosphere where these cation exchanges take place is called a cation exchange site. The number of exchange sites determines the capacity of soil to hold nutrients. This is called the soil's cation exchange capacity. The availability of nutrients is contingent on the soil's pH. What is pH? pH is an abbreviation for the power of hydrogen. The P of pH lets us know the scale is logarithmic, or that instead of counting 1, 2, 3, it would be like counting 1, 10, 100. And the H tells the concentration of hydrogen ions in the solution being measured. And hydrogen is a cation. So on a scale of 1 to 14, the center of the scale 7 is neutral and is based on the number of ions present in pure water. And each step to the left of the 7 shows an increase by 10 times in the number of hydrogen ions present. A pH of 1 would be very acidic. Battery acid. And each step to the right shows a decrease in the number of hydrogen ions present. So a pH of 14 would be very alkaline or basic. And if we, let's see, so if we think about why it's important to know your soil's pH, it's because the pH actually affects the availability of nutrients in your soil for plants. So gardeners typically shoot for a soil pH of about 6.5 to 6.8, and that's the soil sweet spot, and it's where most nutrients are available and where plants and soil organisms do best. Notice in this chart how nitrogen begins to drop off its availability. It may still be in the soil, but its availability drops off when the pH hits 5.5 or so. And look at the impact on phosphorus when the pH is 6. The best way to buffer your soil pH is to add organic matter in the soil. Plants that lack nutrients And if these plants are consumed by animals, including people, the plants will not offer the humans or the animals as much nutrients. And this chart shows the part of the plant that benefits from different nutrients in the soil, as well as the benefit to animals, including humans. So one of the best things that you can do for your garden is to get your soil tested and find out your soil's texture, your soil's pH, the nutrients in your soil, and the organic matter content in your soil. And Rutgers Soil Testing Lab offers homeowners soil test kits where you can collect your own soil sample and mail it in for testing. And there's the website at the bottom of the slide, and I think Karen's going to put that in the chat. And they are currently open for business, although I would encourage you to call ahead to find out their status. And I do believe that spring is their busy time. So call ahead, make sure they're open, taking samples, and send your sample in. I want to address one more element that's been getting a lot of attention, rightfully so, in the past decade and more so now. Carbon. So carbon is everywhere. Carbon is the fourth most abundant element in the universe and is the building block of life on Earth. Carbon exists in pure forms such as diamonds or graphite, or in the millions of different kinds of carbon compounds that scientists have currently identified. We use carbon compounds such as wood to build and heat our homes. Carbon compounds are responsible for combustion in the gas tanks of our cars and in the muscles of our bodies. The small 6-proton atomic element known as carbon is central to life and is critical to regulating our climate. And it can exist in very small 2-atom molecules such as carbon monoxide, CO, up to molecules that contain thousands of atoms such as proteins and our DNA. On Earth, carbon compounds circulate through the atmosphere, the oceans, the land and soil, and all the organisms that live here. All of these components comprise the global carbon cycle. As carbon compounds circulate, they are continually converted into new forms of carbon compounds. Look at this terrestrial food web image. You can follow the carbon through the food web. Carbon atoms move as part of a carbon compound, so they don't move as single atoms. This diagram shows how carbon atoms in carbon dioxide molecules, originally found in the atmosphere, move through plants, through animals, through the soil. Next, consider the simple representation of the global carbon cycle. So these are carbon reservoirs called sinks and sources. The arrows represent the movement of carbon between 4 reservoirs: the ocean, vegetation and land, which includes plants, animals, and soil, fossil fuels, and the atmosphere. Reservoirs store carbon. The numbers within the arrows represent gigatons of carbon moving through the carbon cycle per year. Note that in the vegetation and land reservoir, more carbon is moving into the vegetation and land reservoir than is moving out into the atmosphere. This tells you that the vegetation and land reservoir is behaving as a carbon sink. A carbon source is just the opposite. A reservoir that behaves as a carbon source releases more carbon than it takes in and stores. when we add up all the carbon in the carbon sinks and in the carbon sources, in this diagram, we see that there is more sources moving carbon into the atmosphere than there are sinks capturing and storing carbon, keeping it out of the atmosphere. And the culprit, of course, is the fossil fuel burning and land use. Land use meaning like deforestation or maybe mismanagement of agricultural practices. Soil is an important solution to rebalancing the carbon cycle. Soil is one of the most complicated reservoirs, or we call sinks, of the carbon cycle. Soil and soil microbes are very important to scientists who study the carbon cycle and climate change. And this is because soils store a lot of carbon. As a matter of fact, more carbon is stored in the world's soils than is currently present in the atmosphere. Scientists agree that there are many unknowns about how soil and soil microbes might respond to regional climate change and how any resulting changes might impact global climate change. And for this reason, research is ongoing in many areas of the world. And my message to you is start with healthy soil. Pay attention to your soil. View it as a critical part of your backyard ecosystem. Get your soil tested and don't treat your soil like dirt. And I am happy to take any questions.
Thank you, Becky. That was very, very informative. And we did have some interesting questions, which we tried to answer along the way. But let me just pass some on to you to see if you have some insight for the people who asked. So Jennifer had asked, after you had talked about the no-tilling, she asked how to prepare the soil because she's going to be removing sod and planting a wildflower garden with native seed. So we we went back and forth. We all had a lot of input for her. And let's see, to kind of summarize it, I suggested sheet mulching, but she said she doesn't really have time. And then Sue suggested just raking the surface and using some organic material like compost. And Christine also had some input. But just letting her know that it does take time for something like that to get going and to make sure you protect the bare soil. So I don't know. Do you have anything to add to that? It was a good conversation we had going about that.
Oh, that's great. Well, that sounds exciting that you're going to be turning your lawn into a meadow. Good for you. Yeah, that's a good question about tilling. And I think generally speaking, there's a real push by soil districts and by NRCS, one of our sister organizations, the Natural Resource Conservation Service, to encourage, I'll say maybe large scale farmers to go no-till. That's where a lot of the soil, is continually destroyed, really. For purposes of taking grass out and putting in a perennial meadow, I think lightly tilling it once is not going to be the end of the world, because you're not going to be tilling it over and over and over again every single year. But do know that the tilling will break apart those really important relationships that the fungi have in the soil, and all the relationships between the soil biota. And the other alternative is, I liked the raking idea because the seeds that you plant, I'm guessing wildflower seeds, they're pretty tiny. I mean, I look at my array of native seeds that I have, and they're all really, really small. You don't want to bury them deeply. You want to basically broadcast them, put them, either just broadcast them, toss them onto your soil, the top of your soil, lightly rake them in, or I put my seeds in a bucket and mix them with soil, and that way they have some weight to them, and then I broadcast them into my soil. So that's an alternative. But it looks like, reading the chat, it looks like you had a nice conversation and got some really good ideas.
And then the other question was by Skip. He was asking, he had heard that worms were invasive, and he was just wondering about that. And then Sue had some good answer for him, telling him that a lot of the worms in the United States are actually not native, but also not harmful, except we mentioned the Asian jumping crazy worms that we actually had a talk about last year. So I put the link to our 2021 event page, and if Skip or anyone else is interested, just scroll down and you'll see the title of the talk. It was actually about spotted lanternflies and crazy worms, but it was a really good talk. Yeah.
Mm-hmm.
And
So
that,
yes, I anticipated this question because I do get this question a lot, and it's a question I have as well. And I am, I'll say continually, I'll say, every once in a while, I'll be creating a presentation that includes earthworms, or somebody will ask me about that. So I look it up, and what I seem to find over and over is that earthworms in northern North America are not native, because anywhere that the glaciers came down, which includes North Jersey, earthworms, I guess, either were killed off, or they did not have a chance to evolve in that area. They didn't exist up there. So South Jersey does have native worms, and I was actually looking it up earlier. Is it Lumbricus terrestris? But we do have a native earthworm, and we do have a lot of non-native earthworms as well. Oh, the nightcrawler, I believe, is a native earthworm, or native worm. But yes, there's some non-natives too. So in the north, where there aren't any native worms, there seems to be some real issues with the invasive worms. They're not just not native, they're invasive up there, in the sense that they're aggressively feeding on the leaf litter, the organic matter in soil forests, and decomposing it to a point where it's losing the positive benefits, such as insulation of the soil. So they're chewing it up into these small bits, and it's a detriment to the forests in northern US. So that can be a problem. But here in where I am, in lovely sandy South Jersey, their worms are welcome in my garden here, and not found, I'll say, in huge numbers in our sandy Pinelands area, because it's too sandy there for the worms. They need that organic matter.
I have a follow-up question, because I was once told that by a ecologist, a New Jersey ecologist, that ants are actually the main insect that helps decomposition in areas where they're not native, or worms are not native, including, I think, the coastal plain. But if you know anything more about that, let us know.
That is my understanding as well, and I believe it. I
Yeah.
see all the earth, the ant mounds, in the sandy soil. So they do all the heavy lifting and create the burrows and aerate the sandy soil here. So I agree.
those are the two main topics for our questions. If anyone else has any last thoughts or questions. And just to let everyone know, before you leave next month, April 12th will be our third webinar, Water Wisely, presented by Dr. Steve Urgeau of Rutgers Cooperative Extension. He's an agent with Ocean and Atlantic counties, and he is an expert about watersheds and water. So please join us again, 7 p.m., April 12th for our next one. And you can go to our website, jerseyyards.org, the events tab to register for that. And thank you everyone who has joined us. And please, if you do get the survey when you're done and you leave, just answer just a few quick questions and give us suggestions for topics you might want to hear about in future webinars. Also,
Great,
I want to
thank
thank, oh, thanks, Becky. But I just wanted to thank, I always forget to do that. I wanted to thank Christine and Sue as well, Sue's from Rutgers Cooperative Extension of Ocean County, and Christine is the director of the Ocean County Soil Conservation District. And together, we're all partners on the Jersey Friendly Yards initiative. So thank you to them. They help out at every single webinar. And I'm Karen from Barnegat Bay Partnership, and we host the Jersey Yards website. So there, I covered it.
Good job.
Sometimes I forget to do that. So thanks, everyone, and hope to see you next time.
Great. Thank you. Have a great night.
See you guys soon.
See you soon.